Welcome back to NANDGAME. We are at the end, the processor set of levels. We're going to take everything we've done before, combine it, and make a Turing-complete computer. So let's get started with combined memory. Memory of a processor consists of two 16-bit registers and a RAM unit. So like it says here, the registers are directly accessible by the processor, the ALU, whereas the RAM is used to store a large amount of data. So we'll have our A and D registers, and A star will be a way to write to RAM or to get values from RAM. Okay, so right off the bat, we know we're gonna need two registers and a RAM. We have three flags, A, D, A star. We have X, which is a value, and our clock. Clock is just the signal, so let's just hook those right up. All right, now let's hook up these flags, these three down here. So when the A flag is on, we wanna write X to the A register. So then all I have to do is hook up A to store, and hook up X to X. D is the same thing. When the D flag is on, you want to write the X value to this, we're going to call it the D register. So you can see here, if I want to write, let's say 50 to the A register, move the clock along like that, and there we go, we got 50 in the A register. If we want to write 30 to the D register, turn that flag on, do the clock, and then we got 30 in the D register. Now the RAM is just a bunch of registers tied together. And with our A star flag, we want to write the X value to whatever address is in our A register over here. So like our A register right now has 50, we want to write to address 50 in the RAM. So we hook up the address input to the A register. I guess let's pin it around here so it's a little bit easier to see what's going on. And it looks like 32 is the address. They're just using the hexadecimal value that you can see right here. We want to hook up store to the A star flag, and X goes into the X value here. So now if we want to write a value to RAM, let's say at the 50th place, because that's what we happen to have. Let's say we want to write 10, flip the clock on and off. And now we have 10, the value of 10 you see in binary here, at address number 50. Let's say we want to write to address number 1. We gotta change the value of the A register, cycle that on and off. Now we have 1 in the A register. And let's just say we want to write, let's say 11 in decimal to the A register. We turn the A star flag on and cycle the clock. And now we have 11. Here you see it in binary, it's 1011 in the RAM. All right, so now we can write to RAM. Now we just have to deal with the output here. Again, pretty easy. All we have to do is have the current value of A output to A, the current value of D output to D, and the current value of RAM at the address given by A output to A star up here. And since we're already setting the address by outputting A to the address input, we should get that. All right, so this should work. A register, D register, RAM. And we use the A register to point to whatever address in RAM we want. Check solution, level complete. And this is the simplest possible solution.
ALU instruction. So I is the instruction to the ALU. That's this right here. And then each bit in this instruction will trigger some flag. So like the 0th bit, which would be the one all the way on the right, if it's set to 1, then that would trigger the greater than condition. So we have ALU instructions. So that will determine the output of the ALU, the destination that will determine if this goes into a D or a star. And then the condition will deal with, I think, the jump command here, the J. The X input to the ALU should be D, that's this right here. And the Y input should be either A or A star, depending on bit 12 in the instruction. If bit 12 is 0, then it's A. If it's 1, then it's A star. The R output is the result of the ALU operation, and the J right here indicates if the ALU output conforms to the condition specified in bits 0 through 2, which are the condition bits. Okay, so this is really just about hooking everything together. All right, and we're gonna have to start with the bit splitter here, because this will split out our instructions. I guess we can put it over here, kind of somewhat out of the way. And then it probably makes most sense to hook up the ALU component first. So bit 10 will be the U flag here. Bit 9 is op 1. Bit 8 is op 0. Bit 7 is ZX, and bit 6 is SW. The X input should be D, and the Y input should be either A or A star, depending on if bit 12 in the instructions is 0 or 1. So we can use our selector here, hook up Y to this selector, and this is going to be based on the result of bit 12. So we'll hook that up to bit 12. If bit 12 is 0, then it's A, so we hook up the 0 to A, and the 1 to A star. Okay, and that's the ALU all hooked up, except the R output is going to be always result of the ALU operation, so I suppose we can hook that straight in. All right, let's deal with the conditions next. I think that'll be a bit easier because we can just use our condition component that we built earlier. And we're comparing against the ALU output, so this X should go to the ALU output. Bit 2 is LT, bit 1 is EQ, and bit 0 is GT. And then we can just hook that up right to the jump. And finally, we have to do the destinations. And this is actually less tricky than I thought, I believe, because I assumed that you had to route the results of the ALU into these destinations. But looking at it closer, it looks like these are just flags. These can either be 0 or 1, which means all we have to do is hook these directly up to the bits that control them, these ones right here. So I think this is correct. Let's try it. Oh, yep. So 3 components used. We didn't get the nice message that we got the optimal solution. Although looking at this, I really don't know how we'd make it any more optimal. Maybe we could do something with the select. But either way, I think this is the most straightforward solution to this problem, where we're really just hooking up components that we have previously built. The control selector. So the S flag selects one of 2 sets of inputs for the output. As it mentions, it's pretty simple. If the S flag is 0, then we want to route everything from control bus 0 over here to the output. If the S flag is 1, then we want to route everything from the control bus 1 to the output. So we're really just going to need a bunch of these select components to route our data. So we'll start with R here, hook up the S inputs here. If it's 1, we want R1. If it's 0, we want R0, and we hook up the output to R. And then we'll repeat this process for the remaining 4 just by adding more selectors. And these are just 1-bit selectors since these are just flags. Hook up the S for all of them. Hook up D1 for all of them. Hook up D0 for all of them. And then hook them straight into the output. So pretty easy. We're just routing data. Check solution. And there we go. No doubt there's maybe a simpler, more clever way to do this with NAND gates. But I think we've got the most straightforward solution here, so I'm happy with it. Next level. All right, in addition to the ALU instruction, the computer should also support data instructions. In a data instruction, the instruction value is directly written to the A register. Create a control unit which execute a little typo there, either a data or ALU instruction depending on the high bit of the instruction. Okay, so this is another routing problem. So we have our instruction here. We need the splitter to get the value of the high bit, the 15th bit here. If it's 0, then it's a data instruction. If it's 1, it's an ALU instruction. All right, let's set up the ALU instruction first. For ALU instructions, the output should be as specified in the previous level, and R appear is the results of the ALU operation. Okay, so we have our ALU right here. We get the instruction from there. We can hook up A, D, and A star. And then we can use our control selector here. That might make it a little bit easier. We'll hook up the selector to the 15th bit. And our 1 is the ALU instruction, so we'll hook the outputs of the ALU into the R1, A1, etc. And we can hook up the control selector outputs to the destinations. And that's our ALU hooked up. For a data instruction, the R output should be the I input. All right, so we have to hook up R0 to I here. This is just going to look kind of messy. And the destination should be the A register. So A should be 1. We can just use a NAND because that outputs 1 always if it's not hooked up to anything. And then D, A star, and J flag should be 0. So we can just leave these not hooked up to anything. Okay, so I think we had this all hooked up as specified right here. Let's try it. All right, level successfully completed. Again, another data routing challenge. Not too bad. You just kind of follow the specification on the side panel here and hook it up, and it works. Next level. Computer! We finally made it. We're going to make our CPU. Okay, so we need a control unit. That's right there. We need storage. That's RAM.
that's memory right here. We need a program memory, that's ROM. ROM stands for read-only memory. It's basically the same thing as RAM, only you can't write to it. We need a counter which keeps track of the current instruction address called the program counter. That is just a counter here. And we need a clock unit. So here it says the word at the PC address in the program memory is the I input to the control unit. So what this means first is that whatever is being output by the counter here, a program counter, is the instruction address we want to read on our ROM here. So the output of the counter is the address going into our ROM. And whatever's coming out of our ROM is the instruction that goes into our control unit. Okay, so then it says each clock cycle changes the program counter depending on J. All right, so let's hook the clock in, and we should see if we pulse the program. Yep, the program is just counting up for each pulse. But depending on our J value coming from the control unit, we may want to jump to a different ROM address. So if the J output on our control unit is 0, we want it to just keep counting up. But if it's 1, then the program counter should be set to the value on the A register, which is right here on our memory. That means X will hook into A over here, and our store on the counter will be turned on if J is 1, so we can hook up store to J. And then from there, we just really need to hook up everything else. So on the control unit, A goes to A, D goes to D, A star goes to A star, and then from the control unit to the memory, A goes to A, D goes to D, A star goes to A star, and X goes to R. And then the clock on the memory should just hook up to our clock, and we've hooked everything up. I think this should work fine. Let's try it out. There we go. And we got the simplest possible solution. We have a working computer. Again, another one that's not too bad. We've built the most complicated components, and now we're just putting them on the board and hooking them up to each other. And I think we've got one more level. Input and output. To be of any use, a computer needs to be able to communicate with the outside world. This happens through hardware devices such as a screen, keyboard, touch sensors, network interfaces, and so on. In this level, we integrate with simple hardware devices, a lamp, and a button. Okay, connect a lamp and a button so they can be accessed like a memory address. Okay, so we're going to need a lamp and a button on our board here. The lamp is controlled by bit 0 and 1 of X. When bit 1 is 1, the lamp should get a signal on. When bit 0 is 1, the lamp should get a signal off. Signal should be sent to the hardware when store is 1 and clock signal is 1. Okay, so let's hook the lamp up then first. So the on and off inputs here will be controlled by bit 0 and 1 of X here. So we're going to need a bit splitter. And all the way on the right here, we have bit 0 and bit 1. And we can't hook these up directly, so we only want the signals to go when store and clock are set to 1. So when store and clock are 1, this AND will output 1. So then we can just use a couple more ANDs for each of these bits. If bit 1 is on and this AND for our store and clock is 1, then we want to send an on signal. And if bit 0 is on and the store clock AND is on, we want to send an off signal. Okay, there we go. There is our lamp. Okay, now the button. The button state is shown in bit 15 of the component output. When the button is pressed, bit 15 should be 1. When it is not pressed, it should be 0. Okay, so here we actually need a bit bundler, and we want to hook up bit 15 to 1, and then just hook that up to our output. And there we go. I think this is all hooked up correctly. Let's check solution. There we go. All levels in processor completed. Is there another level? Oh, we got software. I didn't even realize that was a thing. I never noticed. Well, we'll do that next time. We've completed processor. And I guess next time we'll move on to software. So thanks for watching. And I guess I will see you for the next one.